Hi guys, let's get going on vectors. We're going to go through 9.1 and 9.2. I hope you watched the two videos that are already on my playlist. One is a quick introduction to some of the terminology associated with vectors and talking about what the difference is between a vector quantity and a scalar quantity. And those notes were called 9.1 vocabulary, and then this is the PowerPoint for 9.1 and 9.2. And it's going to be focusing on some things that we're already pretty comfortable with, a little bit of notation, as well as some visual representations of how to manipulate vectors. So let's go through this PowerPoint. If I want to highlight something, I'll just circle it with this, and then I might flip over to my presenter occasionally, so you can have some notes or some worked out examples. But let's just go through this PowerPoint. So some of the things I wanted to talk about here is that a vector is represented using a directed line segment. That means this right here. So the vector AB begins at A and ends at B. The vector BA is not the same thing as AB. Okay? Sometimes we put bars around vectors, and that is to represent the term magnitude. Magnitude, for the vocabulary section before, magnitude means size or length. Okay, so size, length, norm, sometimes used to talk about magnitude. The direction of AB is from A to B. B to A is not the same vector because it has a different direction. Two directed line segments, if they have the same magnitude and the same direction, then they are equal vectors. So if I'm looking at A, B, and then maybe this is C, D, E, F, they're all parallel, so they have the same direction, and they all appear at least to have the same length. That makes them all equal vectors. Okay. Sometimes a vector is written AB, and sometimes it's written as a boldface V, or if you notice down here, it's a letter lowercase with an arrow showing the direction on it. Okay, vectors by lowercase boldface, like this. Two vectors are equal if they have the same direction and magnitude. So not equal, same direction, different length, same length, different direction. Here we go, same length and same direction, so they're equal. So here's two definitions I want you to make sure that you get in your notes and annotated if you're just going to print this off. So two vectors u and v are equal if they have the same magnitude and the same direction. And the other thing that you need to recognize is that if I'm discussing a vector u and I talk about the opposite of u or negative u, it's got the same length but it points in the opposite direction. So if we were thinking about slope, then this might have a slope of 5/2, and if this arrow were pointed the other way, you would say that it's negative. Okay, so even though it looks like they're the same thing, if the arrow points this way, it's starting at this end and ending here. One of the terms in the video you watched was referred to as displacement. So there's two things we could discuss with this visualization right here. We could say what is his displacement versus what is his distance traveled. So let's imagine he starts right here, and you could refer to this as negative u and positive v, and then positive u and negative v. So if I added positive and negative, they're going to effectively go to 0, and then these two are going to effectively go to 0. So even though I've traveled 180, that would be distance, my displacement, how far am I from my initial starting point after I travel all the way around? Well, I haven't changed really at all. So my displacement for this question is 0. Vectors can be looked at with displacement, translation in the plane. So this is on the coordinate plane. So here are two directed segments, PQ, that's this one, and RS. U and V are what we're going to call these vectors. Okay? These two vectors can be shown equal because two things are true about them. They both are starting low and ending high, so they have a positive slope. Okay, they're both going upwards, and they're going up 5, 2, and then 5, 2. Okay, and then if I wanted to talk about their magnitude, I could say that the magnitude of this line right here would be 5 squared plus 2 squared square rooted. So thinking about this as a right triangle, and then using Pythagorean theorem to find out the magnitude of vector u. So that would be the square root of 29 here. And then if you think about this also as a right triangle, you can see that the change here is also 2, and the change here is also 5, just like it was here. And that means that it is also going to have a magnitude of the square root of 29. Okay. Component form is a special way that we name vectors. So on the previous one here, this guy right here can be written in component form because he goes from 0, 0 to 2, 5. So if I wanted to discuss vector u, I could just call it 2, 5. However, because vector v does not start at the origin, I could not call it 5, 6, because that would be indicating that it starts at 0 and ends at 5, 6. Okay. For coordinates, so this is u, 2, 5. So if the initial point and the terminal points of the vector of this are the same, right? If it starts and it ends at one point, then it's denoted as bold-faced 0, or the 0 vector. And so its beginning and end point is just 0, 0. Or it could be shifted to the point 0, 0. So another term here, if u is a vector in the plane with the initial point 0, 0, and the terminal point some x and some y, the component form of this vector would be written as the coordinates of x and y, so long as it's starting at 0, 0. Sometimes it's written horizontally with x, y, and sometimes it's written vertically with that x, y. This is u sub 1, u sub 2, but it's still the x term and the y term, the horizontal term and the vertical term. What that means is that any vector, even if it's not starting at the origin here, can be named in terms of its length and height. So this would be u sub 1, u sub 2. So let's say that this is at 1, 2, and this is at 3, 4. Then you could name the difference between the x's and the difference between the y's as the name of u if you wanted to talk about it in component form. Here's an example of worked out one like this. So I have a segment and it starts at -1, 2, and then it goes over to 3, 5, and we're going to call that vector v. Well, if I wanted to draw vector v in component form, talk about its component form, and move it to the position vector so that the end point is, the beginning point is at the origin and the end point is shifted to a place equal to that one or corresponding to that one, then this guy is right here. And then if I'm looking at the difference in my vertical change and the difference in my horizontal change, those two terms become component u sub 1 and u sub 2. So the difference horizontally between these points is 4, and the difference vertically between these points is 3. Careful, the scale here on the x is different than the scale here on the y. That's why it looks a little tricky as 4, 3. Now, if I want to talk about the magnitude of this, I would say, think about that right triangle again. I'm still looking at 4 and 3. So that makes this a special right triangle, one of those ones that's a Pythagorean triple, meaning all three sides are integers. This is a 3, 4, 5 triangle. And if you want to prove it to yourself, 3 squared is 9, 4 squared is 16, That makes 25 when summed. Square root of 25 is going to be 5. So the length or the magnitude of V is 5. Now, if I wanted to talk about the opposite of the vector, well, the opposite of the vector is going to have the same length, but an opposite direction. So it's going to start here at 0, 0, and then instead of going up and over to here, it's going to come down 3, backwards 4. So it would be over this way with it starting here at 0, 0, and then pointing downwards to this point, and it would be read as negative 4, 3. You could also call that negative V. This next section right here starts 9.2, so we're going to start a different video for that section.